Okay, welcome to the lecture series on electronic devices. So today we'll be having some basic revision of module 4, wherein it may help you with the internal assessment, that is IS, right? So this is very important question, wherein you will definitely see this question in your final exam. Definitely, it will be appearing in the final exam, right? So, what is that question? Question may be asked with a neat diagram, explain the construction and operation of uh, JFET, that is JFET, or explain in brief the construction and working or construction and operation of JFET. Okay, so this is short question. In module 4 and 5, you have a fixed number of questions which will definitely appear. Okay, so I say people, those who want to clear with an average of 60 to 70, those people can definitely uh, look into these questions. Along with that, they can study other questions also. I guess in every module I'll be giving few very important questions which will definitely appear in the final examination. Right? So this is one of them. Basic working, basic construction and operation of JFET. So before we start with the operation, let me tell you few lines about the construction. Right? So how the JFET is constructed. In one of the previous classes, I had explained. Am I audible, right?
Yes, sir.
Yeah, and the screen is visible.
Yes.
Okay. So the very construction starts with taking a pure semiconductor. This is the very first step. Almost everywhere we use this first step, that is taking a pure semiconductor. Then you dope it with some material, that is P-type material or N-type material. This will be step number 2. Okay. So I had given an analogy saying that take a bread, take a single bread, and that bread, it will act like pure semiconductor. Then you can dip it in tea or coffee, right? And that dipping in tea or coffee where diffusion takes place, that will turn that pure bread into impure bread, where the particles of tea will be present in the bread, right? Similarly, the second step, we just go with the doping, and that doping will lead the pure semiconductor towards impure, that is either P-type or N-type, right? So let us consider, for example, we are taking N-type semiconductor, that is we are doping pentavalent impurity. After that, what we do? Actually, if you just look at the figure of JFET, it is very clear that we have to again next dope the two extreme ends with the P-type material, right? So what I'm doing, I'm just explaining you N-channel JFET. If the question is reversed, they may ask you P-channel JFET also. Then everything will be swapped. Swapped means we had taken N-type impurity, there we have to take P-type impurity. And here at the extreme ends, we are doping with the P-type materials. There we'll be doping it with the N-type material, right? So first, let me cover the N-channel. Then I'll tell you what changes have to be done, right? So after the two extreme ends doped with the opposite type of material, that is P-type material, what they do, they just simply place the ohmic contacts, and after placing the ohmic contacts, the terminals will be taken outside. Those terminals are called as gate, source, and drain. Right. So this is very brief, very brief about the construction of JFET. Okay, if you go in detail, again, there are so many steps to be repeated in the fabrication process, but these many steps are okay for the exam point of view. I repeat, first step, take the pure semiconductor. Second step, dope it with the N-type material. So that will turn into N-type substrate. Then third point, dope the two extreme ends with the P-type material. Next point, using ohmic contacts, take out the terminals. Okay, take out the terminals. So these are the steps in construction. Next, when we start with operation, right, then we have to consider a few cases. The very first case is VGS equals to 0. What do you mean by VGS equals to 0? The voltage between gate and source, it is 0. Means gate is also, you can think that gate is shorted to source. Though it is not shown here, you can imagine that gate is shorted to source and that source is connected to ground, that is 0 volts. Right? And here in diagram you are seeing here is one gate and here is one gate, right? But basically they will be shorted. So we will having only single gate. So this is the drain, this is the source, and this shorted gate we have single gate, right? And the very first thing is VGS equals to 0. Along with that, VGS equals to 0 condition, we have one more condition, that is VDS is positive. Here you are able to see plus VDS means VDS is positive. Correct. So what happens when we apply VGS equals to 0 and VDS positive? What will happen? So when we increase this VDS, current will start increasing. As you are seeing in the graph, x-axis is VDS, y-axis is ID, that is drain current. As we increase the VDS, yes, current will increase. Correct. But what is fixed? What is constant? VGS we have made it constant. That is, we are not changing the gate voltage. Simply we are increasing the drain voltage. So how will you write this in the form of sentence? In the operation, you have to start with the condition number 1 or case 1. In case 1, you first write VGS equals to 0 and VDS is positive. Below that, you write pointwise. What will be the point? The first point will be the VGS equals to 0 is achieved when gate is connected to source and that source is grounded. VDS is positive means some positive potential will be applied at the drain and that positive potential will be increasing linearly. That will be increased, right? These are the 2 points explaining the conditions. Then what will happen after this condition? That you have to explain. In point number 3, you will be writing as VDS is increased, keeping the VGS constant, we see that the current increases linearly as shown in the graph. And then you have to draw these 2 diagrams. Okay. So this is point number 3. But so next point, fourth point will be, but as VDS increases, what will happen? As VDS increases, what will happen? Here, positive potential which is applied at the N-type material. Okay. So here positive VDS, correct. This positive VDS is connected to N-type material. In center we have N-type material. These 2 ends are P-type. So positive applied to N-type material means it is reverse biased, right? So as we increase the VDS, no doubt the current will increase, but the depletion region near the drain it tries to increase. This is the explanation of case 1, right? Next, go with the case number 2. What is case number 2? You have to draw these 2 diagrams, right? What is case number 2? VGS is minus V1, that is negative, and VDS is positive. Means negative voltage will be applied at the gate with respect to source. VGS minus V1 means what? Negative voltage will be applied at the gate. Again, I am repeating that both the gates will be shorted, right? Though it is not shown here, but actually they are showing with the help of equation. VGS minus V1, VGS minus V1 means what? Both the points are same. Okay, that means they have to be shorted actually. Okay. So VGS is negative, right? When VGS is negative, how it is achieved? You have to explain that first. How that VGS is negative achieved? By applying negative potential at the gate with respect to the source. Correct. Next, how positive VDS? Again, same thing here. You can say positive potential applied at the gate. Positive potential applied at the drain. Right. So this is the condition of second case. Then what will happen? So you have to write, because negative potential minus V1 is applied at the P-type material, it will be reverse biased. Correct? Negative potential P-type, reverse biased. When it is reverse biased, the depletion width, right, the blue color that you are seeing, right, that depletion width will be more compared to case 1. I will show you case 1. See here, the depletion width is less. Why it is less? Because there is no reverse biasing. Zero potential is applied at the P type, right? But what happens in second case? Negative potential applied at the gate. So because of this negative potential, because of that reverse biasing, and which is due to negative potential, the depletion region is more widened compared to the case 1. At the initial stage only. I'm not speaking about VDS here. At the initial stage only, the depletion width is more. Okay, that is due to the effect of reverse bias. Next, what this is case 2, right? What will happen if we increase VDS? If we increase VDS, what will happen? As we are seeing here, the channel width is decreased. Very important point. Depletion width increased means what? Channel width decreased. Right. So the space for the charge movement, it is very less here because of increase in depletion width. So when space is reducing, then less number of charge carriers will move from one point to the other point. Electrons which travels from source to drain, it will be less. Okay. So what will happen? When less number of electrons are moving from source to drain, that means what? Less number of charge carriers passing a point, right? That means what? That means the current level will be lower. This is first case. The straight line, it is first case. Next, dashed line, it is second case. Why the current has decreased? Because space is less. Right? Why the space is less? Because depletion width is more. Why the depletion width is more? Because of negative potential. That is causing reverse bias condition. Understanding?
Yes.
Yes, sir.
So you people have to, just a second. Saturday. Yes, madam. ಒಂದ ದಿವಸ ಐತಿ ಬಟ್ ಇದು ಎಲ್ಲೇನು ಮೇಡಮ್
ಇಲ್ಲೇ ಮೇಡಮ್ ಈಗ ಮಾಡ್ಸೀನಿ ಇಲ್ಲ ಆಗೈತೆ ಏನಿದ್ರು ಅವ್ರು ನೋಡ್ತಾರ ನಿಮ್ದು ಬರೀ ಕ್ಲಾಸಿಂಗ್ ಅಷ್ಟೇ ಸರ್
26 ಅಲ್ಲ
ಹಾಂ
ರಜೆ ಹಾಕ್ಬೋದು ನಾನು 3 ದಿನ ಸಿಗ್ತದಲ್ಲ ಇಲ್ಲೊಂದು ಹಾಕಿದ್ರೆ 3 ಸಿಗ್ತದ ಒಟ್ಟರೆ ಹಾಕ್ತೀನಿ ಗ್ಯಾರಂಟಿ Yeah, so what I was explaining here, I was saying about the current, right? The current, it is decreased. Why? Because there is less space for charge carriers to move. Why there is less space? Because of increased depletion width. Why increased depletion width? Because of reverse biasing. Why reverse biasing? Because negative potential applied here. That is very clear, right? But the other thing, when we increase VDS, yes, the current will increase. Current will increase here as we increase the VDS. Correct. So that thing is very clear, but the level you are seeing here, see at this particular point, the level is here for the second case, but the current level is high in the first case. So these diagrams are very, very important. And explanation, you can write it in your own words. No issues with that, right? But keep in mind, all the diagrams with all the notations, right? They should be very neat so that the evaluator feels comfort in evaluating and gives sufficient, that is maximum marks. Okay, if you are not keeping the answers clean and tidy, then there is a chance that though you have written everything, they'll simply cut the marks. Say if this question is asked for 10 marks, then you may get 7 or 8. Okay, if you are drawing it very neatly, then you may get 9. Right? So all the diagrams are very, very important. All the diagrams you have to draw, right? If you write 1 or 2 sentences less, no issues with that. But you have to draw all the diagrams neatly, right? So what is happening in the next diagram? What is happening here? V2, VGS equals to minus V2. So here V2 means what? It is more negative. Okay, V1 was somewhat negative, say minus 1 volts. But if I increase that, minus 2, minus 3, right? That means I'm increasing the negative potential at the gate, more reverse biasing. That is leading to more reverse bias condition, and that more reverse bias condition, it is causing increase in depletion width. And what we are seeing here, the channel is blocked, and when channel is blocked, there is no space left, then the current is zero. We are seeing here, right? So if you take intermediate, say the voltage which is between V1 and V2, then the graph will be in between. Okay, it will, the current level will be lower, right? It will be like this. Understanding?
Yes, sir.
Yes, sir.
Yes, sir.
This is very, very important question. Okay, it will be asked for 10 marks. So I'm going very slowly so that you understand each and every aspect. And I'm explaining. It is like I'm dictating notes only. I'm explaining each and every point, how to write the answer. So here what we'll write. When a more negative voltage is applied at the gate, that will lead to more reverse bias condition. And as a result, the depletion width will increase. Next point, due to increased depletion width, there will be no space for the charge movement, or there will be no space left for the charge to move from source to drain. Hence, the current level will be almost zero. As am I audible?
Yes, sir.
Yes, sir.
If it is visible, right?
Yes, sir.
Okay. Sorry. Again, there was a network error. I'm going slowly here. Why? Because this is sure short question in the exam. For 10 marks, this will be definitely asked. Okay. This question cannot be skipped. Okay. So this point is clear. Yes or no?
Yes, sir.
Yes, sir.
Next, again, we are going back to case number 1. Okay. So here what you have to explain. You have to draw each and every diagram. Okay. It will take time. I understand. But you practice in such a way that you have to draw it quickly with neatness. So again, we go with the case number 1. Only one or two sentences you can write again in case number 1. As explained earlier, right? In case number 1, as we increase the VDS, the current is rising linearly. This is only one point to be explained here. Nothing much. Because we have already explained case number 1. Then next diagram, you have to go with the changing depletion width. How to explain that? So as VDS is increased, correct? As VDS is increased, the drain side, the drain terminal becomes more reverse biased compared to the source terminal. Hence, the depletion width near the drain becomes more widened. And channel will be decreased. Channel width will be decreased, right? And because there is a decrease in channel width, what we are seeing, the current, it is not linear. Exactly, it is not linear now. Okay, it is changing. Why it is changing? Why it is not going straight? Because of this. Because the channel width is decreasing. The graph is showing us change in current. Okay, why there is change in current? Because there is change in resistance. There is change in resistance. So when P equals to I into R, right? When R changes, yes, the I will also change. So when R increases, here R is increasing because width is decreasing, right? So when R increases, the current will decrease. Decrease in the sense it is not increasing up to the mark, correct? So only this point you have to explain here. Next point is, as we increase VDS more and more, the drain terminal becomes more and more reverse biased, so that the depletion width near the drain, it almost touches each other. That condition is called as pinch off condition. I hope you remember, it is called as pinch off condition. As explained in the graph, after pinch off condition, the current will not increase, but it will saturate. And the region where the current is saturated, it is called as saturation region. Okay. Understanding?
Yes, sir.
Okay. So all the diagrams are very, very important. Okay. All the diagrams will have 1 mark each. So starting from here, 1, 2, 3, 4, 5, and 7. 7 diagrams are there. Right. So for diagrams, you'll be having 5 to 6 marks. For explanation, you'll be having 4 to 5 marks. So this point is clear. Then we'll go with the next diagram. So here what we are seeing, if the VDS, that is applied voltage at the drain, if it is increased more, that is, it is crossing the VDS saturation. What is VDS saturation? the voltage at which the saturation has happened, the pinch off has happened, that is VDS saturation, this voltage. If we go beyond that, if we go on increasing the voltage beyond that, then this condition will happen. Means the depletion region will start overlapping, right? And it is called as phase charge region. So this delta L, it is called as phase charge region, right? So this total length, it is actually L should be the length of the channel, right? So this L is length of the channel, and from that length, some space is being wasted for space charge region. Right? So ideally speaking, space charge region should be lesser and lesser, because if it is increasing, then current will be obstructed. So this is, as I said, very sure question for 10 marks. We'll go with the next one. Yeah, this is also one of the very, very important questions. Small signal equivalent model of JFET. It will be asked for 6 marks. Okay, for 6 marks, it will be asked. So you have to draw all the 4 diagrams. So this is JFET, right? This is the cross section view. If you cut the JFET, then it will be looking like this. First, you write down what is the meaning of small signal equivalent model. So before that, you can even write what is equivalent model. Equivalent model is a model, or it is a combination of circuit elements chosen properly, which actually which actually describes the behavior of the component, right? That is equivalent model. What is small scale equivalent model? Small signal equivalent model. Small signal equivalent model, it is a model where for analysis we just apply small signals. Okay, we just apply smaller signals for the analysis. So this is the cross section of JFET with source and drain series resistance. Why the series resistance here? See, every material has some resistance. Okay, likewise, whatever material we are using here, it may be N type or P type, right? It also has some resistance, internal resistance. That is nothing but source and drain series resistance, right? And how this we have drawn? How we have drawn the small signal equivalent model of JFET? So, as explained earlier, between each terminal, we have one capacitance that is called as parasitic capacitance. Capacitance between gate and drain, it is called as CGD, right? Capacitance between gate and source is called as CGS. Capacitance between drain and source, it is called as CDS, right? So these three are unwanted parasitic capacitance. We have one more capacitance called as CS, that is connected at the only source. Then in between the terminals, we also have resistances. So like here we have RGS, this is RGS between gate and source. Then we have RGD, then we have RDS. Apart from that, we have series resistance of RS and RD. This is RS, this is RD, right? And what is this? This is a constant current source. Why we are writing constant current source here? Constant current source, from where to where it is shown? It is shown from drain to source, correct? So as we have seen earlier, that the current will flow from drain to source. Electron will move from source to drain, correct? Electron will move from source to drain. So current will move from drain to source. So in view of that, we are taking constant current source from drain to source. And why it is a constant current source? Why? Because we know that after saturation, the current will remain constant. Okay, so at that time, JFET will behave like constant current source. And when we try to neglect few of the things here, which are very, very small, actually these parasitic capacitances, these are very, very small in value, maybe in terms of picofarads. Okay, very, very small, 10 raised to minus 12. So these can be neglected, correct? And gate and source, they are not connected actually. Gate and source, they are not directly connected. So here what we are showing, there is no connection between gate and source, or you can think that the input resistance of JFET is almost infinite. If you say ideally, the input resistance of JFET, it is infinite. What do you mean by input resistance? The resistance which appears from the input side. Which is the input side? Gate is the input side. Source is common. Output side is drain. Correct. So from input side, if we see the resistance, then that resistance is called as input resistance. And for JFET and for MOSFET, ideally speaking, the resistance is infinity. Input resistance is infinity. Okay. So here we are not showing any resistance. Means between this point and this point, nothing is there. Nothing is there means what? Nothing is there means resistance is infinity. If you keep two hands, what is there between two hands? You can say that, yeah, there is air between the two hands, right? But between the two hands, which are kept apart, the resistance is infinity. And here what we are taking constant current source. This cannot be neglected. Why? Because it provides some current from drain to source, right? Actually, the current flows from drain to source. And what is this? This is RS. RS, it is source resistance. Okay. But again, if you try to simplify it, actually you can ignore this RS, right? If you try to ignore this RS, then your diagram will look like this. Nothing is there. Nothing is there. Gate and source, nothing. Drain and source, only constant current source. Correct? So this is the small signal equivalent model of JFET. We use this circuit. For some analysis, we use this circuit also. We can ignore RS and we can consider the effect of RS. Okay, actually RS effect will be there. But if that effect will be negligible, so we can ignore the effect of RS. Right? So here what we will be explaining. First you say what is about equivalent model. What do you mean by equivalent model? Then you say what do you mean by small signal equivalent model of JFET. Right? Then you have to draw all the four diagrams. PPT is visible now.
Yes.
Okay. So I was saying about small signal equivalent model. For every diagram, you have to explain 2 to 3 sentences. Here you can explain a bit more. Right here, what you can explain: the parasitic capacitances exist between each terminal. That is CGS between gate and source, CDS between drain and source, CGD between gate and drain. Likewise, even internal resistance between the terminals, they also exist like RGS, RGD and RDS, right? Along with that, we have internal series resistance RS and RD, which are shown in the diagram. Then this constant current source, it represents the current flow from drain to source, right? But the effect of these values, they are very, very small. Like these values are very, very small. So the effect of those can be neglected, and simplified equivalent circuit can be written as shown. So the third diagram you have to write, and here you have to write the effect of RS is very negligible. Even that can be ignored, and the more simplified version will be looking like this, right? And what is this? This is a constant current source by name GM into VGS. GM into VGS, right? So what is this indicating? What is this telling? It is telling that this constant current source, it is dependent on VGS. What is VGS? VGS is input voltage between gate and source, right? So this voltage can change the current. If you change VGS, current will change. Why? Because current is nothing but GM into VGS, and hence this JFET, it is called as voltage control device. Right? It is called as voltage control device. And few equations you have to write if asked, right? If it is asked, or otherwise also you can write the equations, right? So here are the equations. IDS is what? GM into VGS, right? Here, this is ID, right? This is ID or IDS. That is nothing but GM into VGS. So this thing you have to write. Then directly you can write this equation. Or if you want to simplify, then you can simplify here, right? So some relation is given between VGS and VG dash S dash, right? What is that difference? VGS and VG dash S dash. What is the difference? One is with the source resistance, and one is without the source resistance. Correct. So what? There will be minor change. No doubt there will be minor change, but that change is shown here, right? This graph also is saying the same thing. That minor change. When we consider the source resistance RS, then this dashed line, lower line will be visible. What is this line? This line is nothing but this is VGS, right? So what is transconductance? What is the unit of transconductance? It is MHO. That is reverse of ohms. Okay. So what is transconductance? It is reverse of resistance, right? So what you are seeing here, if the effect of RS is seen, then current will decrease a bit, right? Because that resistance RS, it will increase the total resistance. Very simple concept is there. If this resistance RS is taken into consideration, the current level will be bit lower. If we ignore the effect of RS, the current will be higher. That is what shown here. And in terms of equation, it is shown here, right? So these equations, this equation you have to write. The first equation, second equation, and at least the final equation. And this step you can write or you can ignore it. Along with that, you have to draw the graph. Correct. So what is this? This final thing you have to remember. This final equation, maximum cutoff frequency, you have to remember. Right. there is no need to remember each and everything here. But final equation, you please remember and just write it in the exam. If you write it for 10 times, you'll remember it. Okay. So actually in detail it is not given. How this G is E into mu n into nd into WA by L. That is not given actually, right? So you just try to remember this final equation, right? So today I have covered even one problem may be asked, right? If they will ask this problem only, which is given in the textbook. Okay. So this thing, if you remember the formula, then it is very simple, easy to solve it. And if it is asked, it will be asked for 4 or 6 marks. For 4 marks, at least for 4 marks, it will be asked. Okay. So today I have covered two very important questions, that is working of JFET, operation of JFET, and small signal equivalent model. Both the questions are short questions for exam point of view. Is it okay?
Yes. Sir,
Do you have any questions for me?